they have what they need, they're quite happy. But in general, the trend that we're talking about here, within the same group, ionization energy is decreasing. Across the period from left to right, the ionization energy is increasing. Okay? So these two arrows, that's something that we want you to memorize. I will give you a list of elements in the periodic table. I'll say which list, in which list we'll see an increase in ionization energy. Well, you have to arrange them. You have to be able to determine the relative location of those elements there. And say, if the list goes silicon, phosphorus, and sulfur, well, left to right, and sulfur will have the highest ionization energy. Okay? But if I give you silicon, nitrogen, and oxygen, well, silicon has a lower energy than carbon, ionization energy than carbon. Okay? Carbon has a lower ionization energy than nitrogen. So if I give you a list of silicon, nitrogen, and oxygen, oxygen will have the highest ionization energy, followed by nitrogen, followed by silicon, because silicon has even lower energy than carbon, ionization energy for carbon. Carbon is the lowest in this group there. So when I give you the list of the elements there, they may be in the same period. In the same period, it's quite very easy, but they also may be scattered around, not within the same period, not within the same column. So you have to look at the relationship there. Remember, going from left to right, ionization energy is increasing, top to bottom within the same group, and ionization energy is decreasing. So you need to be able to judge for a list of elements there, and you need to be able to arrange them in the order of increasing ionization energy, decreasing ionization energy, depending on where they are. And remember the general rules there. Now, when you use the general rules to answer questions there, especially when you do your homework in this part of the textbook there, in this part of the class there, you will see whatever you come up with may not be what the answer gives you in the textbook there. Not that you did something wrong. You are using the general rule. And it could be a situation in the textbook there, there's an exception. Why the exception? Well, each exception has a different explanation associated with it. Okay, so this part of the homework there, what I want you to do is that as long as you remember or memorize the general trend, you're good. And if you do the question there, if you try to answer the question in the homework there, you didn't get the correct answer there, just pay attention to what the correct answer is in the textbook there. And take some time and read the textbook there. And if you can figure out why, that's great. If not, then just remember the general trend. Okay, so that's the ionization energy. So the periodic trend for the first ionization energy increase across the period, left to right, and decrease down the group there. Why? Well, that's always the question we always want to ask. Why do we have this particular trend? Because the electron ionization energy refers to the process of removing electron. Removing electron has something to do with the electron-nuclear interaction, because the electrons are being attracted to the positive charge center. Okay? We call it effective nuclear charge. It also has something to do with electron-electron repulsion. Because if you only have one electron, that electron only experiences one type of force. It's been attracted to the positively charged center. But if you have two or more electrons, those electrons are, many of the electrons are within the same room, in the same model, or on the same energy level. They are also interacting with one another, and they all bear negative charges there, so the electron can repel. So the electron repulsion versus the electron nuclear attraction or effective nuclear charge, these are the things that determines the amount of ionization energy required. So by definition, effective nuclear charge, Z with the star there, is the nuclear charge experienced by a particular electron is actually modified by the presence of other electrons there. Okay, so the effective nuclear charge is decreasing from top to bottom in the same group, and it's increasing from left to right within the same period, and that's the reason there. So when we have, remember electrons are being categorized in core electrons versus valence electrons. So if you have core electrons present, like in hydrogen, you don't have core electron. Hydrogen has one electron, and you have the positively charged center there. But if you go to lithium, lithium has 3 electrons. Okay, the two electrons, the first two electrons are what we call the core electrons. Those electrons, those two electrons are closer to the positively charged center, essentially blocking part of the attraction between the nucleus and the third electron, the valence electron. So removal of that electron is easier. The effective nuclear charge is decreasing, comparing hydrogen and lithium. So removing that electron becomes easier. If you go to sodium and potassium, one step at a time, going down from top to bottom in the same group there, well, you're going to have a decrease in effective nuclear charge. The valence electron is further away from the positive charge center, making it easier to remove the electron, hence the general trend. So we need you to memorize the general trend and to understand why the general trend, well, the reason behind that trend. Well, that's great. If you don't memorize, if you don't understand the reasoning there, at least memorize the general trend. Okay, so the effective nuclear charge is decreasing down the group there. As a result, ionization energy is decreasing. But within the same group though, within the same period though, N has the same value. You would have more and more electrons packed on the same energy level. Those electrons are closerly held, if that's a word in English, and they're held much more closer than the fewer electrons. As a result, the effective nuclear charge is actually increasing. There's a stronger attraction. So going from metal to non-metal, it becomes more difficult to remove electron. It takes more energy. Hence the trend, going from left to right. The ionization energy is increasing. Within the same period, the ionization energy is increasing. Okay, so what about electron affinity? Well, electron affinity, in terms of periodic property there, electron affinity follows the same trend, the general trend. Now, this is something that we talk about. Ionization energy is always endothermic. Okay. Electron affinity can be endothermic, can be an endothermic process, can be an exothermic process. But in general, top to bottom, when you try to attach electrons to a gas-phase elements there, atoms of gas-phase element there, well, the ionization, well, electron affinity is decreasing from top to bottom, increasing from left to right. Okay. So it follows the same trend. And this is something that I need you to, minimum requirement, memorize. Try to also understand the reason behind that. And for the ionization energy, we talked about the effective nuclear charge. And for the electron affinity there, in general, again, top to bottom within the same group, it's going to be decreasing. Left to right, it's increasing. That, again, is the general trend. We do see the gaps in there. Okay, the second group there, the third group there, the fifth group there. And there's exceptions to those general groups there. But in general, electron affinity increases across the period. Now, when we say the word, when we use the term across the period, we always refer going from left to right. Okay? That's by convention. And normally when we say across the period, we're talking about going from left to right, and then decrease down the group there. Okay? So that's the periodic trend for ionization energy, electron affinity. What about the size of the atoms there? Well, this picture indicates the radii of different elements or main group elements there, group 1A all the way through group 7A. Let's say we leave group 8A out.